Welcome all. Today we begin one of the most important foundations of automotive engineering, vehicle dynamics. Vehicle dynamics deals with how a vehicle moves, accelerates, brakes, turns, and responds to driver inputs. It combines physics, mechanics, and mathematical modeling to predict and improve vehicle behavior. Whenever you turn the steering wheel, press the accelerator, brake hard, or go over a bump, the vehicle experiences a complex interaction of forces and moments. As engineers, we should be able to model these forces, quantify them, and then design systems that control them. Today's session will cover three major areas. First, the basics of vehicle dynamics. Second, the fundamental modeling approaches, including the lumped mass model, the bicycle model, and an introduction to the 12 degree of freedom model. Finally, we will discuss the forces and moments acting on a vehicle with mathematical expressions and solved examples. These performance metrics quantify how effectively the powertrain translates driver inputs into vehicle motion, while maintaining stability under standardized test simulations. Acceleration time, lateral acceleration, yaw rate, braking distance, and ride comfort indices together help refine vehicle performance across different speeds and road surfaces, ensuring responsive, stable, and comfortable operation. Vehicle dynamics in simple terms is the study of how vehicles move in the real world. We look at three major behaviors such as longitudinal dynamics, which describes the motion in forward or backward direction. For example, acceleration, braking, and traction. Lateral dynamics, which describes the sideways motion, for example, cornering, turning stability, understeer or oversteer. Vertical dynamics, which describes the up or down motion, for example, ride comfort, suspension response, and vibration. Every movement of the vehicle is governed by Newton's laws of motion. Fundamentally, we use the relationship force equal to mass times acceleration. This governs acceleration, braking forces, cornering forces, and aerodynamic forces. To analyze vehicle motion, we first define a coordinate system. This coordinate system follows the Society of Automotive Engineers, or SAE, reference frame. The x-axis represents the longitudinal direction, which is the forward motion of the vehicle. The y-axis represents the lateral direction, and it is positive toward the left side of the vehicle. The z-axis represents the vertical direction, pointing upward. Vehicle rotations are described as moments about these axes. Rotation about the x-axis is called roll. Rotation about the y-axis is called pitch. Rotation about the z-axis is called yaw. These coordinate systems are essential for accurate mathematical modeling of vehicle dynamics. Let us begin with the forces acting along the x direction. The most important force in this direction is the tractive force. We know that force multiplied by distance gives torque. Rearranging this relationship, we obtain the tractive force equation. The tractive force Ft is given by Ft equals Tm multiplied by Eta divided by Rw. Here Tm is the motor torque, Rw is the wheel radius, and Eta represents the drivetrain efficiency. This equation forms the foundation for analyzing vehicle acceleration and launch capability. It also plays a critical role in the proper sizing of the battery, motor, and gearbox. The drivetrain efficiency determines how much motor torque actually reaches the wheels. It is influenced by several key factors, including the powertrain type, transmission losses due to gear friction and hydraulic slip, differential gear, and bearing friction, and losses in driveline components such as CV joints and additional shafts in all-wheel drive systems. Efficiency also varies with the motor or engine operating point. Lubrication temperature, control systems like torque converters, and overall vehicle configuration. In low-fidelity models, drivetrain efficiency is treated as a constant, typically 0.9% for electric vehicles and 0.85% for internal combustion vehicles. In high-fidelity models, drivetrain efficiency is modeled as a dynamic quantity that depends on torque, speed, gear selection, and temperature. Aerodynamic drag is given by the expression Fd equals 1/2 times rho times Cd times A times V squared. Here rho is the air density, Cd is the drag coefficient, A is the frontal area, and V is the vehicle speed. Rolling resistance is given by FRR equals CRR times M times G, where CRR is the rolling resistance coefficient. A simple numerical example shows that aerodynamic drag becomes significant even at moderate speeds, and rolling resistance must be included for accurate vehicle modeling. We also observe that rolling resistance is independent of speed. In contrast, aerodynamic drag varies with the square of velocity. As a result, doubling the vehicle's speed leads to a fourfold increase in drag force. This drag force ultimately limits the maximum achievable steady-state vehicle speed. The example provided here helps us to understand the fact that by calculating the traction force, drag force, and the rolling resistance forces, we can understand the accelerating nature of the EV, which in turn predicts the launch and passing performance. The drag coefficient is governed by vehicle geometry, surface quality, and airflow management. Streamlined shapes with rounded fronts and tapered rears reduce wake formation. Smooth surfaces, lower ride height, wider stance, and flat underbodies help limit turbulence. Enclosed wheels, sculpted wheel arches, flush-mounted accessories, and active cooling shutters further reduce aerodynamic drag. Final refinement is achieved through wind tunnel testing and computational fluid dynamics, or CFD, across different vehicle speeds. As a result, typical drag coefficient values range from 0.19 for advanced electric vehicles, 0.23 to 0.28 for sedans, 0.30 to 0.40 for SUVs, and up to 0.45 to 0.70 for trucks. The rolling resistance coefficient, CRR, represents the energy lost when tires deform and rub against the road. It mainly depends on tire material and construction. Softer rubber increases losses, while stiffer belts and sidewalls can increase or reduce CRR. Rolling resistance is also affected by tire pressure, tire width, tread pattern, vehicle load, road surface, speed, temperature, wheel alignment, and bearing condition. Typical CRR values range from 0.006 for low resistance tires to about 0.030 for off-road tires. The braking force, FB, is generated by the braking system and acts opposite to the direction of motion. This force is limited by tire road friction and is given by the expression FB equals mu times m times g. There is no direct mathematical relationship between the rolling resistance coefficient, CRR, and the road grip, mu. However, tires designed for higher grip usually have higher rolling resistance because increased tire deformation leads to greater energy losses. The lumped mass model represents the vehicle as a single rigid body, with all its mass concentrated at the center of gravity. This model is commonly used for basic acceleration analysis, aerodynamic load estimation, and braking distance calculations where all forces are summed and applied at the center of gravity. The vehicle's longitudinal, lateral, and vertical motions follow Newton's laws of motion. Rotation about the vertical axis, known as yaw, is modeled using the yaw moment of inertia and yaw rate, which links the applied moments to vehicle rotation. The lumped mass model is the simplest dynamic representation of a vehicle. In this model, the rotational effects, suspension motion, wheel dynamics, and load transfer are neglected, assuming straight line motion on a flat road with simplified tire road interaction. Despite these assumptions, the model is highly valuable for rapid analytical speed calculations, early performance targeting, control prototyping, and initial vehicle design forecasts. Rearranging Newton's law gives the vehicle acceleration as acceleration equals Ft minus Fd minus Fr divided by m. This shows that acceleration increases with higher tractive force, decreases with aerodynamic drag and rolling resistance, and reduces as vehicle mass increases. This compact expression allows quick trade-off studies between powertrain output, aerodynamic design, tire technology, and vehicle mass reduction strategies. Aerodynamic drag increases with the square of vehicle speed, meaning that doubling the speed results in roughly 4 times the resisting force. At high velocities, drag can balance the available tractive force, reaching an equilibrium where traction equals drag and rolling resistance, and acceleration becomes 0. This condition defines the vehicle's maximum steady-state speed and highlights the critical importance of drag coefficient and frontal area in achieving top speed targets. The equation v squared equals u squared plus 2as links the final speed to the initial speed, acceleration, and distance traveled without involving time. This equation can be viewed as an energy per unit mass balance for constant acceleration motion. The squared velocity terms represent kinetic energy per unit mass, while 2as represents the work done over the distance traveled. Let us start with acceleration. A equals dv by dt. Using the chain rule, we change the independent variable from time to position and write acceleration as a equals v times dv by ds. Now we separate the variables, giving v dv equals a ds. Next, we integrate both sides. Applying the initial conditions, s equals 0 and v equals u. This leads us to the final result, v squared equals u squared plus 2as. To determine the stopping distance, we set the final velocity to 0 and assume a constant deceleration. This simplifies the motion equation to s equals minus u squared divided by 2a. This expression directly links stopping distance to initial speed and braking capability, and it forms the basis of vehicle braking analysis and highway safety design. If we replace deceleration with mu times g, the stopping distance becomes s equals u squared divided by 2 mu g. This shows that doubling the speed results in 4 times the stopping distance, while higher tire road grip reduces stopping distance linearly, a rule drivers experience intuitively. By neglecting load transfer, suspension flexibility, wheel dynamics, and rotational motions, this simplified model cannot accurately capture vehicle handling, stability, or ride comfort. Its accuracy reduces during aggressive maneuvers, on uneven road surfaces, and under high-frequency inputs. For these conditions, higher fidelity vehicle models are essential for detailed chassis development and safety critical validation. This model is best used for early-stage performance targets, powertrain sizing, preliminary energy consumption estimates, regulatory braking assessments, and initial control algorithm development. When the focus moves to lateral dynamics, ride comfort, or safety critical validation, higher fidelity multi-body or coupled models should be used to ensure efficient use of computational and development resources. The bicycle model is widely used for steering and stability analysis. The concept is simple. The left and right wheels of the front axle are combined into one equivalent wheel, and the same is done for the rear axle. This model is used for understeer and oversteer analysis, yaw stability, and lane change dynamics. The lateral and yaw moment equations for the bicycle model are shown above. For a clearer understanding, let's explore the bicycle model using a real bicycle as an example. Motion is described in a body fixed frame with x forward, y to the left, and z upward. The vehicle state is captured by lateral velocity, v sub y, yaw rate, r, and a constant longitudinal speed, v. Vehicle geometry is defined by distances a and b from the center of mass to the front and rear axles, while mass m and yaw inertia I sub z quantify resistance to translation and rotation. The lateral tire forces, Fyf and Fyr, act as the primary inputs driving the dynamics. According to rotational Newton's law, the sum of yaw moments equals yaw inertia times angular acceleration. The lateral tire forces produce moments about the center of mass through the lever arms, A and B, generating a net moment that initiates or resists turning. This fundamental law links microscopic tire forces to macroscopic vehicle rotation, forming the basis of the first governing equation. The front lateral force, Fyf, pulls the vehicle nose sideways with moment arm A, generating a positive yaw moment. At times Fyf, the rear lateral force, Fyr, acts oppositely with arm B, producing a negative yaw moment, B times Fyr. The difference, Afyf minus Bfyr, is the net torque that determines whether the car understeers, oversteers, or maintains neutral steer. This torque directly leads to angular acceleration. Combining these, we get Iz times rate of yaw equals Fyf minus Bfyr. This equation predicts yaw acceleration from instantaneous tire forces. A larger front moment accelerates the rotation into the turn, while a larger rear moment resists it. Designers adjust A, B, and tire cornering stiffness to achieve agile yet stable handling, important for emergency lane changes and autonomous path tracking. The net yaw moment determines the vehicle's tendency to rotate. Positive yaw moment indicates a net rotational tendency to the left. Through the simple problem, we understand that the sign and magnitude of mz is critical in understanding steering response, such as understeer or oversteer characteristics. During a turn, the tires generate lateral friction forces toward the center of the curve, providing the centripetal acceleration needed to counter the vehicle's inertia. The required lateral grip is given by m times v squared divided by r equals Fy. If this demand exceeds the available friction, the vehicle will understeer or skid. Since lateral force is limited by Fy less than or equal to mu times m times g, the maximum safe speed becomes Vmax equals the square root of mu times g times r. This relationship guides road design, speed limits, and tire selection, showing that tighter curves or lower friction require reduced speeds to maintain safety. Yaw rate provides a direct geometric description of the vehicle's path. The path curvature is given by kappa equals small r divided by v, and the corresponding turn radius capital R equals v divided by small r. This kinematic relationship offers an intuitive view of steady turning and naturally leads to the familiar centripetal acceleration expression v squared divided by capital R. This slide combines the previous steps into the compact expression lateral acceleration, a y equal to lateral velocity plus r times v. The term r times v represents the centripetal acceleration generated purely by yaw motion. Even when the lateral velocity is constant, the vehicle still experiences sideways acceleration because the velocity vector is continuously rotating. Applying Newton's second law in the y direction equates the sum of lateral tire forces Fyf plus Fyr to mass times the composite acceleration, which is lateral acceleration plus centripetal acceleration. Rearrangement gives the second governing equation. This relation shows that any imbalance between front and rear side forces directly generates both sideways motion and yaw, explaining why steering feel and stability are inseparable phenomena. Two equations encode rotational and translational Newtonian balance for a simplified yet powerful vehicle model. They reveal how tire forces simultaneously generate yaw and lateral motion, explain understeer versus oversteer, and serve as the computational heart of modern stability and autonomous driving systems. The lateral and yaw motions are intrinsically coupled through the same tire forces acting at the front and rear. A steering input changes tire slip angles, which simultaneously alters the net lateral force and the yawing moment. As a result, maneuvers such as lane changes naturally involve both sideways motion and heading change, requiring control systems to coordinate lateral and yaw dynamics together. Omitting the v times r term removes the physics of curved path motion from the model, leading to underestimated lateral forces and inaccurate handling predictions. Including this yaw-induced centripetal effect is therefore essential for correctly capturing both steady-state cornering and transient vehicle response. Full 14 degree of freedom vehicle model is the most complete. It includes 6 degrees of freedom for the body, 3 translations and 3 rotations, plus 4 wheel rotational degrees of freedom and 4 suspension degrees of freedom. This model is used in high-end simulations and advanced driver assistance systems, a DAS, for practical teaching and basic calculations. The bicycle model and lumped mass model are more commonly used. The sprung mass refers to the portion of the vehicle supported by the suspension, including the body, passengers, and powertrain. This sprung mass possesses 6 degrees of freedom, longitudinal, lateral, and vertical translations, along with roll, pitch, and yaw rotations. Using Newton-Euler equations, the applied forces and moments are related to linear and angular accelerations. forming the foundation for modeling how the vehicle accelerates, corners, rides over bumps, and responds dynamically through lean, dive, and rotation. An E5 wheel is where opposing effects meet. The electric motor applies a driving torque, while the tire road contact resists it through a longitudinal force acting at the tire radius. The wheel's rotational inertia sits between these two influences, determining whether the wheel speeds up, slows down, or maintains constant rotation. When the applied motor torque exceeds the resisting tire torque, the wheel accelerates and traction is produced. When the motor torque is lower, the wheel slows down, corresponding to braking or regeneration. When both torques balance, the wheel rotates at constant speed, representing cruising. These three cases directly describe traction, braking, and steady driving, giving engineers a clear physical guide for wheel control. Each wheel adds its own rotational motion, governed by the balance between applied torque and tire force given by inertia times d omega divided by dt equal to ti minus fxi times r. These wheel dynamics explain slip behavior, ABS action, traction control, and torque vectoring. The wheel speeds feed into tire models to determine driving and braking forces, linking the wheels with the vehicle body, and enabling advanced stability and autonomous control systems. Sprung mass includes all components supported by the suspension, such as the vehicle body, powertrain, passengers, and cargo, and typically accounts for about 85 to 90% of the total vehicle mass. Because it is isolated from road disturbances by the suspension, it moves more slowly and largely determines ride comfort. In contrast, unsprung mass consists of components below the suspension, including wheels, tires, brakes, and parts of the suspension itself. Making up roughly 10 to 15% of the vehicle mass, it responds directly to road irregularities and plays a critical role in maintaining tire contact and precise handling. When a wheel encounters a road bump, the unsprung mass responds first, moving rapidly with the road surface. The sprung mass follows more slowly, filtered by the spring and damper. This interaction illustrates how the suspension isolates occupants from harsh road inputs while allowing the tire to maintain continuous contact with the road. The suspension system is characterized by three elemental parameters: the suspension spring stiffness Ks, the damper coefficient Cs, and the tire radial stiffness Kt. The spring and damper act between the sprung mass and the unsprung mass, controlling body motion and isolating vibrations. The tire stiffness connects the unsprung mass directly to the road surface, which is treated as a displacement input. For clarity, tire damping is neglected, leaving the tire as a purely elastic element. Together, these parameters determine the force transmission and vibration frequencies experienced by both the passengers and the road. To draw the free body diagrams, think of the car body and the wheel as two separate masses connected by a spring and a damper. When the body moves higher than the wheel, the spring and damper push downward on the body and upward on the wheel. The wheel also feels an additional force from the road through the tire. We take upward motion as positive and spring compression as positive for analysis of forces in the suspension division. These forces are the only vertical forces acting on each mass, allowing us to directly apply Newton's law to describe the suspension motion. These boxed equations describe the vertical dynamics of the sprung and unsprung masses. The sprung mass equation contains only internal suspension terms, representing how the body responds to spring and damper forces. The road input appears exclusively in the unsprung mass equation through the tire stiffness term, acting as the single external excitation. Together, these two equations capture the fundamental trade-off between ride comfort, governed by body motion, and road holding, governed by tire contact. Suspension behavior is explained by Newton's second law applied to the sprung and unsprung masses. This leads to a set of linked equations that describe how the vehicle balances ride comfort with maintaining tire contact on the road. This basic quarter car model forms the foundation for more advanced full vehicle simulations, control system design, and performance trade-off analysis. Now, let us discuss vertical dynamics, which are associated with bumps, potholes, and suspension behavior in electric vehicles in a simplified form. The suspension force is given by Fs equals Ksz plus Cs times d divided by dt, where we ignore the mass effect and vertical acceleration. Here, Ks is the spring stiffness, Cs is the damping coefficient, and z is the suspension deflection. The tire vertical force is Fz equals Kt times Zt, where Kt is the tire stiffness and Zt is the tire deflection. These forces determine ride comfort and road holding. The 14 degree of freedom model combines body motions, wheel rotation, and suspension movement to give the most complete picture of vehicle dynamics. This high level of detail makes it ideal for a DAS and autonomous vehicle development, where accuracy is critical. However, because it is computationally demanding, it is best used for offline simulation, while simpler models are preferred when faster analysis or clearer insight is needed. Finally, let us consolidate the essential force and moment expressions: tractive, drag, rolling, cornering, suspension, and yaw into a concise mental toolkit. Mastering these fundamentals allows a deeper understanding of stability control, ABS, and autonomous path planning in the upcoming sessions. To conclude, vehicle dynamics is the science of predicting how vehicles behave under real-world forces. We learned how to model a vehicle with basic equations, understand aerodynamic, rolling, cornering, and suspension forces, and apply mathematical expressions to analyze acceleration, braking, and turning behavior. In advanced vehicle engineering, these equations form the foundation of ABS, traction control, electronic stability control, and autonomous vehicle motion planning. Thank you, and we shall meet again in another topic on EV powertrains in the next video.